In this lesson, we're going to look at objective 6.7, bond enthalpies. So the learning objective states that we should calculate the enthalpy change of a reaction based on the average bond energies of bonds broken, that's reactants, and formed products in the reaction. So if you're thinking, are we talking about chemical bonds? We sure are. So in these types of problems that you're going to be seeing, we can solve for an actual delta H like we saw in 6.6 based off all the different bonds in the reactants and products. Now, every single type of bond takes a specific amount of energy to either break or form it. So we actually take the difference of the reactants sum and the products to get our overall delta H. You would have to be given these bond energy values unless you're solving for them. But we'll talk more about it when we look at the type of examples that you might see. Okay, so during a chemical reaction, bonds are broken and or formed, and these events change the potential energy of a system. So the average energy required to break and form bonds can be estimated, okay? So our reactant molecules, we're adding up the average bond energies absorbed. So again, to break reactants, we need to absorb energy to break those bonds. And then to make our products, we're going to add up all the average bond energies that were released, because when we form bonds, we release energy. So if the energy released is greater than the energy required, in that case, the reaction is going to be exothermic. So that's talking about energy released products is greater than the reactants. The reaction's exothermic. But then if the energy required reactants is greater than the energy released products, the reaction is endothermic, which is positive. Now the equation for this to solve for the actual delta H based off, again, we're taking the sum because we're adding up all the different bond energies of the reactants and products. Here we can solve for the delta H by taking the difference. But this one is not on your equation sheet. So the delta H of reaction, I'm going to zoom in over here, is here taking the sum, that means sum. We take into consideration our stoichiometric coefficient. So here the delta H of bonds broken, so this is our reactants, minus the sum of all of our bonds formed. This is our products. Here, this again is not on your equation sheet, but here we do bonds broken, reactants, minus bonds formed, products. You will see if you're like, but hey, I'm looking at my equation sheet and I'm seeing products minus reactants, that's going to be over objective 6.8 using formation values. Here we're using bond energies, okay? So if you can kind of see the chart below peeking out at the bottom, here this is just a chart I found online of some common bonds that we will see. So you can see all the single bonds on top, and then at the very bottom has the multiple covalent bonds. So like a double bond carbon, triple bond carbon, but you can see that the single bonds move into double and triple are increasing because it's going to require or release more energy. All right, so let's look how to solve for the first one. So here we're going to solve for the delta H of reaction. That's essentially what it is. You can also, like I say, see it like this, which we've seen earlier. Here we can solve for our delta H reaction using the chart to the right. But how I like to start this off first is sometimes you have to draw what you're working with. So here NH3 ammonia is drawn like this. Again, there is a coefficient 4 here. Then we have 3 oxygen. Here, oxygen is going to be a double bond. Then the nitrogen is a triple bond. Then we have 6 waters. Now, if I went through that too fast and you're like, I don't remember how to do that, you need to go back to 2.5, Unit 2 and Objective 2.5. That's Lewis structures, okay? Sometimes you are going to need to draw out what's happening. So here, to start this off, we need to look at what type of bonds we see in our reactants. So I see from the NH3, I see a nitrogen-hydrogen bond. But if you notice, I have 1, 2, 3. I have 3 in one single NH3 chemical compound. I have 3 NH3, but there's 4 ammonias. So 4 times 3 is 12. So I have 12 NH bonds. Then for the oxygen double bond, I have 3 because there's just 3 of them there. That is all for our reactants. Now it's time for our products. So again, how I'm writing this is I'm thinking about our equation, bonds broken minus bonds formed. And here I'm just laying it out based off how many bonds just to help me later. Then I have a nitrogen triple bond, and based off the coefficient, there's only 2 of them. And then for the water, I see some OH bonds. I see 1 and 2. But the issue is, based off this oxygen single bond to the hydrogen, there is a coefficient of 6 waters. So 6 times 2 is 12 OH bonds. All right, so now moving on here, I can start plugging in some values to start finishing off the problem. So the nitrogen-hydrogen bond is 390. The oxygen double bond is 498. Then moving on to products, the nitrogen triple bond is 945. And then our oxygen-hydrogen bond is 460. Here, adding all of this up, you do get the delta H of the reaction as negative 1,236 kilojoules per mole of the reaction. So this would be an example of how we can get a delta H for a reaction. So like we learned in 6.6, how we were given a delta H, but then we were like, oh, but what if we only have 5 grams of it? Here, this is what's giving us our constant. So scientists use Bond enthalpies. I will say there's a more effective way and more accurate approach of getting a delta H reaction, but if you only had Bond enthalpies in front of you, this would be one way to actually solve for it. All right, so I have this problem for you right here. This has given you not more of a molecular, but more of a structural formula, just kind of easier to draw out how big it is. But here, why don't you pause the video, right? Do this yourself. First draw it, and then I'm going to try to show this up here in case you need to reference it. You don't have guided notes in front of you. But yeah, draw this out, find out what kind of bonds we're working with, then use that chart and do reactants minus products, okay? So yeah, pause the video and try this out yourself. Right, so when I first started this problem, I drew out all 3 of those structures. I then first laid out how many bonds I was working with. So I saw 6 CH bonds. I saw 1 carbon-carbon single bond, 1 carbon double bond, and 1 hydrogen single bond. That was for all the reactants. And the products, I had 8 CH bonds and 2 single carbon bonds, okay? Now, what you could have done is actually crossed off and simplified, because there are a lot of matching values on either side if you really, really wanted to. But overall, there was only honestly a change of negative 6 kilojoules per mole. This reaction didn't release overall that much energy, which is totally fine. But overall, what I would do is just make sure you draw out the structures correctly. It wouldn't even hurt to sometimes circle how many you're working with, just to make sure that you've accounted for every single bond in that actual structure, especially taking into consideration the coefficient.